Alright, so now we're going to do some three-point mapping. So here we're going to map 3 genes at a time instead of just doing 2-point mapping where we map 2 genes at a time. We can use 2-point mapping to map 3 genes, but we would have to do 3 different crosses. So if we had 3 genes A, B, and C, we'd have to do an AB cross, AC cross, and a BC cross, and then put all those 3 maps together. But in this way, we can, if we do a 3-point map, we can just do one cross, and then we can look at the data and figure out the distances between the genes. It gets a little bit tricky, and it also lets us start thinking about double crossovers and that sort of thing in meiosis. So a triple heterozygote means that it is triple heterozygote means it's heterozygous for 3 things. But if I draw it like that, we don't know exactly how it's a heterozygote. So we can still have the different coupling configurations. So A and B could be coupled, A and C could be coupled, A and B could be in repulsion, and you can have any of those combinations. So that's one of the things we'll have to figure out from the data. And then we're always going to do a test cross like that. So we're going to take something that's triply heterozygous, and we're going to do a test cross for something that's homozygous recessive for all 3 genes. But like I said, there could be lots of different ways that this could be a triple heterozygote. So the easiest way is all the big letters on one side of the line and all the little letters on the other side of the line. In this case, A and B are coupled, B and C are coupled, and A and C, everything's coupled. But it could also be something like this, where we got a little c on top and a big C on bottom. So A and B are coupled, but C is in repulsion to the other 2. You could have B and C together and something like that. And all the different ways that you can think of getting those are possibilities. We also can get things in different orders. So one of the things that we're going to have to do is figure out what order these genes are in. So here I've written it as if A, B, and C are in that order, but it could easily be A, C, B. And if it's A, C, B, you could have A, C with a little b, and a little c, big B. So you could have something like that. So here we're saying C is in the middle. And we've got 2 possible different, these are called arrangements. So like coupling or repulsion arrangements. We've got some different ways that they can be arranged on the chromosome. So we got to figure that out. But we can also have, so we could have B in the middle, we could have C in the middle, but we could also just as easily have A in the middle. So we could have A in the middle, B on one side, C on the other. Or maybe, excuse me, we could have something like this. So A's in the middle. And when I use these letters and say A's in the middle, I mean the gene A is in the middle. I don't necessarily mean the big letter A is in the middle. I mean it is, but we're just talking about the A gene. So A's in the middle, C's in the middle, B's in the middle. So the first thing we have to do is we have to figure out which genes are on which side of the line. So what is the arrangement, and then which gene is in the middle. So those are the first 2 steps. And then we can figure out the distance between the genes. So another thing about these types of crosses is no matter what, if you're triply heterozygous for something like this, you can get 8, you always get 8 different kinds of gametes. Just draw them all out here, and you have a big A, little b, little c, little a, big B, big C. And you could have A, little b, big C, and little a, big B, little c. So I think those are all different. So we've got A, B, C, all the capital letters, and then all the little letters. And then A, B, and a little c, little a, b, big C, big A, little b, little c, little a, big B, big C, and then big A, little b, big C, little a, big B, little c. So we've got all 8 of them. And where do these things come from? Well, if the genes are not linked and they come from independent assortment, you'll get all 8 of those in equal proportion. So 1/8 to 1/8 to 1/8 to 1/8. Because that's just like it's a trihybrid cross in that case. But if the genes are linked, it kind of depends on how things started out. We'll represent it here in sort of the simplest case scenario. So we'll look at it, how we get these different configurations if we start out with big A, big B, big C together, and little a, little b, little c together. So all of the genes are coupled. Big A and big B are coupled, big B, big C are coupled, big A, big C are coupled. So if we get no crossing over, we'll get, so these are going to come out in different classes. So no crossing over occurs, and these are gametes. We can just get that chromosome, and we can get that chromosome. So these are going to be our non-crossovers, which are also our parentals. But then we can start getting crossovers between these things. And if we get a crossover between, we kind of draw a crossover like that. Now big A is going to be connected to little b and little c, and little a is going to be connected to big B and big C. So that was these guys. So big A now is with little b, little c. So big A with little b, little c, and little a with big B and big C. That was this guy. So keep those down here. Big A went with little b, little c, and little a went with big B, big C, because we had a crossover here. So that's called a single crossover. They're both single crossovers. And these are single crossovers between the A and the B genes. So just between A and B. And it doesn't matter if we use a big A or a big B here, we're just saying between the A and the B locus. So both of these are the result of a single crossover between A and B. If we get a crossover between B and C, then little a, little b, and big C are connected. So little a, little b, and big C are connected. So I guess I should do it over here. So little a, little b, big C, little a, little b, big C, big A, big B, little c. And so these guys, I'll just move these guys over here. So big A, little b, little c, little a, big B, big C. These are also single crossovers, but in this case they're a crossover between B and C. If we get a double crossover, so we're going to get this crossover and we're going to get this crossover. We looked at the chromosomes before, and what happens is big A now is going to go with little b and big C. So big A, oops. So if we get a double crossover, we get little a, big B, little c. Or big A, little b, big C. And so if you look at these and you compare these double crossovers, so these are double crossovers. So there's a crossover between A and B and a crossover between B and C. It looks like the big B and the little b switch sides. They just kind of, the stuff in the middle flips. So in a minute, what we'll see is that we can actually use the double crossovers to try to figure out which gene looks like it flips sides, and that'll tell us what gene is in the middle. So when I'm drawing it out like this, we're already telling you what genes are in the middle. telling you what the arrangements are. Um, but and then we can predict what happens with all these crossovers. But when you first do the cross, you don't know any of that information, and you have to actually figure that out from the data. But in this particular case, we know that these are the parentals. Each of these are single crossovers, and these are double crossovers. What we also are going to know is that, so if we weren't told this, so just like when we did other crosses, we can tell what the parentals are and all the crossovers are if we tell you ahead of time, or you can figure it out from the numbers. And the parentals are always the most. So whatever's the most is going to be the parentals. Now in this case, the single crossovers will each be less than the parentals, but the double crossovers will be even less than those. So the double crossovers will always be the lowest number. And that's because it's less likely to get two crossovers between A and B and between B and C. That's just less likely. If you have a 10% frequency of crossing over between A and B and a 20% crossing over frequency between B and C, the probability, so that would be a 10% for a crossover between A and a 20% or 20% probability of a crossover between B and C. The probability of getting both those things is 0.1 times 0.2 is 0.02. So the double crossovers are way less frequent than everything else. And so we can look at that information to figure out sort of our starting point. We can identify the parentals, and then we can use that compared to the ones that are the least, and we can figure out what our double crossovers are and everything else. And so I'll do one other example. I don't want to write all the possible arrangements, but I just did that case with big A, big B, big C. But let's say we started out like this, with a little c, and a little a, little b, big C. Now our parentals will be big A, big B, little c, little a, little b, big C. These will be the parentals, because we know they're starting out that way. So they'll be the most. If we get a single crossover between A and B, now we'll get big A, little b, big C. Big A, little b, big C. And we'll also get little a, big B, little c. That's a crossover between A and B. If we get a crossover between B and C, just between B and C, we'll get big A, big B, big C, little a, little b, little c. So these were single crossovers between A and B. These were single crossovers between B and C. If we get a crossover between both, the one in the middle is still going to flip. So B is going to flip down, big B is going to flip down to the bottom, little b is going to flip up to the top. So then, if big B goes down to the bottom, then it'll be little a, big B now, big C. And on top, it'll be big A, the little b that just flipped up there, and the little c that was there. These are double crossovers. Now, and these will be the least. So we're going to use this information. So we're not going to be given this. We're going to be given all this data. We're going to be given the numbers for this, and then we have to figure that out. All right. Let's do one more example of another possibility. Let's say that A is in the middle. Let's say we got B, A. We'll do a hard one, just so you can see what these things look like. Make little c, little b, little a, big C. If that was the case, then our parentals would be big A, big B, big A, little c, little b, little a, big C, parentals. Single crossover between A and B, or between B and A, would be now big B, little a, big C, because we're just picking these guys up. Little b, big A, little c. If we get a single crossover here, now we're going to have b, little a, little c, little b, little a, little c, big B, big A, big B, big A, big C. So now this was a single crossover between, we'll say B and A this time. Single crossover between A and C. And then our double crossovers, the A in the middle is going to flip sides. So now we'll have big B, little a, little c, little b, big A, big C. So here you can see that whereas up here we've got big A on top, little a on the bottom. If we just flip those, it'll look like these guys. So that's where these parentals and double crossovers come from, and these will be the most, and these will be the least. Alright, so that's just kind of the concepts behind it. We can look at the end of this, and we'll draw out some chromosomes to show what these double crossovers are looking like and how we get these things with our if we actually look at the chromosomes. But for now, we will just continue forward. So how do you do these things? So here's an example. And you're usually given some ambiguous information. You're given information that says a triple heterozygous female is test crossed with these results. And you should always get these kinds of results. So you should always get 8 things. If you get less than 8 things, that means one of those things is a 0, and you can write down that category and just call it 0. But you should know what 8 things are going to potentially come out of here. So one of the first things you can do is list the genotypes. Well, first of all, we have to pick an order for what genes, for what order the genes are in. So we're going to have to write a bunch of stuff down. And we don't know what order it is, so we'll just pick an order, and then later on we might have to change it if there's 3 possible orders. In this case, black could be in the middle, hooked could be in the middle, or dumpy could be in the middle. The way they wrote these out, they're writing it out with, like, if you look at this one down here, it says dumpy, black, hooked. So we'll keep that one in the middle, and that'll be our starting point. Now that doesn't necessarily mean it's the right starting point, so that's important to keep in mind. Alright, so now this one, we need to look and see what are the most. So well, first of all, we can list all the possible genotypes. So wild type is plus plus plus. Dumpy, black, hooked. I'm going to write that one out so I can keep the order. Dumpy, black, hooked. These guys are just black, so there's not a whole lot of room here. So we're gonna have to make these a little bit bigger. So what I'm gonna do, I'll write them down here, and we'll put the numbers back in there. So we got plus 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 is 169. And we're going to say we could actually reorder them if we really wanted to, but I'll leave the order the way they are right now. And then we've got black, and this is saying that black's in the middle, even though we don't know black's in the middle. We just want to keep the order. So our order is dumpy, black, hooked. And then the next one is black and hooked. The next one is dumpy, which is over here, and hooked, which is over here. Another one that's just hooked. We got one that's dumpy, black, hooked, dumpy, black, and just dumpy, because we're just dumpy over here. And then if their mutant isn't designated, then the other guys are wild type. And so it's going to be best if we can put this one in here. Plus plus D. So plus plus D. Then we'll put in our numbers, 19. 301, 21, 8, 172, 6, and just dumpy is 305. So which one are the most? 301 and 305 are the most. So those are our parentals. So that tells us that plus, black, and hook started on one side of the line, and plus D started on the other side of the line. That's because this guy's a parental, this guy's a parental. Got black, we started out black hooked and dumpy. So what that means, when we made that heterozygote, we took a black hooked fly and crossed it to a dumpy fly. And then we got black hooked over dumpy. So we don't know the order yet, but we know the arrangement of the alleles, and that's always the first step. Just look at your parents, and that tells you where we started out. But any of these three genes could be in the middle. So we could have plus HB over, so we're putting H in the middle. Now let's do that a little bit differently. So we can put H in the middle, but we'll put B over here. So this is just another possibility. And then that would be plus D. Or D could be in the middle. So if we put D in the middle, then these genes are over here, and we'll keep B to the left and H to the right. So these are three possible ways that this thing could be heterozygous. Each of these cases, we still have B and H on one side of the line and D on the other side of the line, but we just have different things in the middle. So what we want to do is look and see if we have a double crossover. What would we get in each of those cases? And we know what the double crossovers are over here, because our double crossovers are going to be the least. So the 6, and I had a 5 somewhere, or an 8. No, I have an 8. So that's a double crossover, and that's a double crossover. So we want to see which of these gives us those kinds of crossovers. We'll start over here on the right. If we get a double crossover here, this D is going to switch sides, and it'll go up to BDH over plus. This one, H is going to switch sides, so we'll have B over plus HD, and this one we'll get plus H over, well not really over, but plus BD. So these are the types of gametes that would come out of double crossovers if each of these things were true. So then we just compare these to the things that we know are the double crossovers. And down here, H by itself and DB together are the double crossovers. So that means this one. So that means these are our double crossovers. That means we started out like this. So here's an important part of the problem. Once you figure that out, so this guy is B on one side, HD on the other side. That's not what our double crossovers look like. This one's BDH altogether, and plus. Here's a plus and a DBH, but those aren't the right numbers. So the ones that are the lowest are double crossovers, and they match this guy. So get rid of this, because that's just going to confuse you. If you're not confused already, you probably are. This is a confusing kind of situation. But now we've done the easy part in my estimation. We've figured out that plus BH over plus D is the right order and the right configuration, meaning that we know which alleles are on which side of the line and which one's in the middle. So then we just have to figure out what our single crossover frequencies are, because we're doing mapping, In mapping, we just need to get number recombinants over the total. And we want to get a map, in this case, we want to get a map between, we need to get a map between something's wrong here. Start over from here. Delete all this. Alright, so here's an example of a 3-point cross. We're going to map the distance between 3 genes and make a little map. The genes that we're dealing with are black, dumpy, and hooked. So this is the infamous black, dumpy, hooked example. And you get to say black, dumpy, dumpy, hooked, black, hooked. You can say that stuff a lot. And so it can get a little crazy. And so what we're trying to figure out is we're doing mapping, so we're going to need to know the number of recombinants over the total for different combinations of things. So that's always our map distance. And then we're going to come up with some map with the 3 genes. We'll have one of the genes in the middle, one of the genes on one side, one of the genes on the other, and we'll have distances. We'll have some numbers in between those genes. But we have to figure out all that stuff. We have to figure out what's in the middle and what order the genes are in, and we can get that from the data. So this thing says the first step is to pick any sequence or order of the genes. So this one has it written down with, if you look at the one where all the mutants are listed, it says dumpy, black, hooked. So we'll use that as our order of genes. So that may or may not be the right order of the genes, but for now we need to start with something, so we're going to start with that. And then the next thing to look at is, I would actually not write out all the genotypes just yet. The next thing to do is identify the parentals. So these guys are parentals, and these guys are parentals. So the ones that are the most are the parentals. So the 301 goes with black, hooked, and the 305 goes with dumpy. And this thing says we're doing dumpy, black, hooked as our order. So what the parentals mean is that dumpy starts out by itself, because that's the parental chromosome, because those are what the parental offspring look like. And then black and hooked, we'll put black and hooked on the other side, and we'll put a plus for dumpy. So that's, right now, that's our suggested order of genes. And then we can write out genotypes for all of these other phenotypes. So wild types can be plus for all genes. Black, we said black's in the middle, so black will get that, and the other two will be plus. Black and hooked, and a plus for dumpy. Dumpy and hooked, with a plus for black. Just hooked, plus for the other two. Dumpy, black, and hooked. Dumpy, black, plus, and just dumpy. Alright, so those are the orders. And I'm going to put the numbers down here too. So 169, 19, 301, 21, 8, 172, 6, 305. Alright, so we already did the first part. We said that these are our parentals. And that tells us which guys are on which side of the line. But we don't know the order yet. We could have 3 possible orders. So this is an order with black in the middle. Let's put dumpy in the middle. And then we can put black over to the left. Now it doesn't matter. The only thing we know about orders is which one is in the middle. So we say black is in the middle in the first case, dumpy's in the middle in the second case. In the third case, we could say, well, what happens if hooked is in the middle? So we'll put hooked in the middle, and then we'll put black over here and plus over here. And then they always have to be opposite. So the mutant allele has to be opposite the wild type allele because these things are heterozygous for all these genes. So these are possible orders. And we know those are just all the three possibilities, but the one thing we do know is that D's on by itself on one side of the line and B and H are together on the other side of the line. That's important. That every cross will be different. So this is where you have to do a bunch of different examples. And the only way to figure out which is on which side of the line is to look at the parentals, and that'll tell you which ones started out together. Now we want to find which ones in the middle. And so now we can take advantage of that little thing we've seen a couple times, that if you have a double crossover, the gene in the middle seems to sort of switch to the other side. So let's do an example, and we'll start over here on the right side, and we'll do an example with this one. So if we have a double crossover, now plus in H, and then H and D get connected together. So the H in the middle flips sides, and we get plus HD, and we'll also get B plus plus. So those are the types of gametes that we would get if we had a double crossover between B and H, if it was in that order. In this case, if we did a double crossover, we'd get plus 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 B B D H, B D H, and plus plus plus. If we got a double cross over here, we're going to get DB plus and plus plus H. The B is going to switch sides, so now D, B, and plus will be together. Plus, plus, and H will be together. So these are possible double crossovers. So we want to know which of these is right. So we look over to our data, and we look at the ones that are the smallest numbers, and these are going to be our double crossovers. So plus plus H is a double crossover, and DB plus is a double crossover. So plus plus H and DB plus. So these are the correct ones. So that tells us that this was the correct order. Alright, so we're almost done. So that just tells us our starting point. Now we can get rid of all this stuff, because that's going to confuse us. And we can rewrite our starting order, D plus plus over plus B H. And then the question is, how many crossovers do we get between D and B? And how many crossovers do we get between B and H? And we can add those up, and then that will give us our number of recombinants over total. So now, if we get a single crossover, so we want to look at our single crossovers. Oh, stopped reading. So if we get a single crossover there, then D, B, and H will go. So that's a single crossover between D and B. So now D, B, and H go together. And plus, plus, plus go together. So over here, plus, plus, plus is 169. And DBH is 172. And we're going to add those up. If we had a single crossover between B and H, so now we're going to cross over here. Now D plus and H go together. And plus and B are together. But then it crosses up there and gets a plus. So it'll be plus B plus. So D plus H is dumpy hooked. So we could actually even just look at these numbers up here and say, oh, which one's dumpy hooked? That's 21. And just black is 19. So these guys go together because they're similar. And you'll always see that the similar numbers go together because 19 and 21 are close, similar numbers. They go together. And then this 169 and 172 will end up going together. So then we have to add them up and get the number of recombinants over the total. But there's one little trick, one last little trick that we have to do. So now the distance between I'm going to erase all this stuff up here. So we just do some calculations at the end. Alright, so I'm going to rewrite. So what we know is, put our cross back up on there. So we knew that from our parents that we had plus BH, and it actually turned out to be in the proper order when we started out. So we'll have to see another example where it's not in the order, so we can change that. But we need to now get the number of recombinants over the total. And a single crossover between D and B counts as a recombinant between D and B. But a double crossover also counts as a crossover between D and B, because that's got a D and B, it's got a crossover between D and B and D and B and H. So we just add those all up. So this distance is going to be 172 plus 169 plus the double crossovers are 6 and 8 over the total of 1001. Couldn't have made that 1,000 just to make life easy. So let's see. Get my handy dandy calculator out here. 172 plus 169 plus 14, because that's 6 plus 8, divided by 1001 equals, well, that can't be right. So 172 plus 169 plus 14, that's 355, divided by 1001 equals 0.354. And so 0.354, and we know that B is in the middle, so we can say D B is 35.2 map units. The other one is 21 plus 19, but we also have to add in the double crossovers. Also divide that by 101, 1001. 21 plus 19 plus 14 is 54. Divided by 1001 is 0.053. And this was 0.352. And so this is 5.3%. So the distance between B and C, or B and hooked, is 0.53. So that's the map between those guys. Oh, it's kind of a long haul to do all that, but it works, and you come up with a map, and it's somewhat useful. All right, so let's just do one more. I think, well, there's we could even do that one again. There's another way to do it, so maybe we'll come back and do that one again. But here's another example. This one's a little bit, it's got some different symbols in it, but we can go through the same process, and I'll try to go through it a little bit quicker. All right, so this one wrote all the genotypes down for us, so that's helpful. And it also organized everything for us into the different types of things. So we know that these are parentals, these are double crossovers, these are single crossovers that go together, these are single crossovers that go together. The only thing that we don't know is which thing's in the middle. And so, because we know these guys are single crossovers, but we don't know what they're single crossovers between. And so these genes are vermilion, cross veinless, and cut. So let's figure out which one's in the middle. So first things first, figure out what's on what side of the line. So our parentals are telling us that V, CV plus, and CT plus go together, and V plus, CV, CT go together. Our double crossovers have V, C plus, and CT together, and V plus, CV, and plus together. So kind of a quick way to think about this is to look at our starting point and say which guy has to switch sides to give us our double crossovers. If the V's switch sides, then the V plus C plus will get all the pluses together, but that's not what we get. If the CV's switch sides, then the CV plus will come down to the bottom, and we would have V plus CV plus together and cut together. So it would be plus plus CT, just cut by itself. And that's this guy up here, so that's not it. So if cut switches sides, now CV plus will be by itself. So if we had a double crossover, if I just look at this, I can say, I can say over here that here's what my double crossovers are: V, CV plus cut, and V plus CV CT plus. So those are the double crossovers. So that's the data, that's our observation. Then which guy's got to flip sides to get us there? Well, if the cut flip side flips down here, then V plus, so if we write this like this, with the cut switching sides, so that cut's on the bottom now. Now these two pluses are together, so the V plus and the C plus are together, so they look like this, and these guys look like this. So that tells me that cut's going to be in the middle, because it's the one that switched sides to give us the double crossovers. So we're going to rewrite our starting point with cut in the middle. So we still have to have the same alleles on the same side of the line, so the cut plus and CV plus have to be on the same side of the line. And then V plus can be down here, and then CV and cut are down here. So this is our starting point. That takes practice. Usually when I give these problems, I let you sort of do it step by step, so that if you can identify the parentals as single crossovers and double crossovers, you can get partial credit. If you can't figure out which one's in the middle, your map will be a little bit off. well, it'll be completely off because the things will be in different order. So now now we want to figure out our crossovers between V and cut, which is in the middle. And if we get a single crossover between the V and the cut, now V, CV, and CT will be together, and all the pluses will be together. So all three mutants together is 89, and all wild type together, plus plus plus, is 94. We'll also have to put in the double crossovers because we always do that. Then we're going to have a distance between cut and let me fix my starting point over here. So the starting point is V, cut's in the middle. Double check what I just did then. So if that's the case, yes, so we still have all three mutants go together and all the pluses go together to give us that. Now we're going to do a single crossover here. So now V plus and CT will be together, and then we'll come up, cross over, and get that one. So we'll get V plus CT CV plus, and if we go the other way, V and CT plus together, and then come down and pick up that one. Now that kind of looks a little bit better for how we draw these things. Now we've got V CT plus CV. So CT plus by itself is the easiest one to look for. That's this one, CT plus by itself, and then the other two guys together, 45 and 40. Now you can, once you know that these numbers go together, the only two numbers you have left are 45 and 40, so you know those go together. And then we just add these things up. 89 plus 94 plus 8 divided by 1448 equals 183. That can't be right. How come? I must be missing a decimal point in there or something. 89 plus 94 plus 8 divided by, so that's 191, divided by 1448 equals 0.131. So V to CT is 13.2. CT to CV so my pens decide kind of get going out on me. So CT to CV are these other numbers together. 45 plus 40 plus 8 equals 93 divided by 1448 equals 0.064 or 6.4. And so this is CV down here. Whoops, that was supposed to be a circle. And so that is the map. We can redraw it down here maybe if we're lucky. V cuts in the middle. CV's down here. 13.2, 6.4. All right, so I'll stop that there. We can do another little one that shows um, how the chromosomes are involved in double crossovers and that sort of thing.